Okay, well, welcome to Physics 8B. It's not a music class, but I like to start with that. The music was Fanfare for Common Man. If you have any suggestions for music that's appropriate to the course, I would like your suggestions of any style, but appropriate. And we'll play some. This is information about where to find help from me. Some of you already found me on email, and that's good. Our head GSI, Chiani, is not here today, but he'll introduce himself one of these days. First thing I want to tell you about is, in case there is an emergency of some kind, fire, earthquake, whatever, the best way to get out are through the lower doors, because they lead outside the building. If you go through the upper door, you're still inside the building. You'd have to find another way out. So if just in case, please go out in an orderly fashion. We'll be okay. And the other tip I give you is that this is a tough course, and you're in a tough series of courses. I'm sure this is not your only course. You'll be under a lot of stress this semester, I'm sure, unless you're either taking it very easy or taking it very hard. But the chances are you'll be under stress, and you will. But don't take it too hard. And if you feel really stressed, there's help at the Tang Center and other places. So do your best, and everything will work out just fine, I'm sure. A lot of you are interested in your grades. We try to distribute the grades approximately A, B's, and C's. Hopefully nobody will be lower than that, because you're all smart people and hardworking. Roughly in this distribution, it works out that way, usually pretty well. A's 25%, 40%. But the problem with this system, frankly, is that it makes you competitive with your neighbor. You say, I want to get an A, and if I'm in the 25%, and maybe she's in the 25%, and that sort of thing. Please don't think of it that way. Try to work together as much as possible, because that's a very good way of learning. And the fact is, you're really not competing with your neighbor. The one you're competing with is the people at Harvard and Yale and Stanford, because they're going to be taking the GRE also and the MCATs. So you want to be you want to do better than they, and you will do better if you study and do well and learn more. I mean, your grade here counts a little bit toward your grade point average and so on, but that's really not the basic deep thing. So I would say work with your neighbor in as cooperatively as possible, learn from each other, and I think you will find you learn more and you will prosper. The other thing I would make a point about my particular approach to the course is that some people are a little bit afraid of math, but that shouldn't frighten you in this course, because although physics has a lot of math in it, and I'll point out where it's a good thing, I try to mostly emphasize the concepts. And if you can understand the concepts, you'll do very well in the course. And, well, we have the Mastering Physics finally straightened out today. If you've tried it yesterday, you probably were frustrated. But, I'm sorry. But the Mastering Physics is up and running now, thanks to some help with from some students. And that is our course ID, and you need your SID, your student identification. Now, the idea is you want to go to discussion groups. I keep touching something and it goes away. There we go. Now, discussions are very good because, you see, we're a big class, and it's hard for you to talk to me every time, whereas in a small group of 20, you can talk to the GSI, you can get to know you. It comes in very handy, especially if later on you want a recommendation. Well, your GSI knows you quite well. I might get to know some of you. I'd like to know all of you by the end of the semester, but that's probably not going to happen. Not my fault. I'm open to meeting everybody, but I know you're busy too. So get to know your GSI. Go to GSI. Ask questions. Go to office hours. Don't be shy. Although this is a big university and big class, you can make it a small university by focusing in on and taking advantage of all the opportunities. As I mentioned, there's some more. Now, the midterms will be, they're already scheduled. They'll be in the evenings of these days. So don't make any appointments for those days. And as I say, I find talking to people is very good, especially if you try to teach something to somebody, because when you hear it coming out of your mouth and it sounds stupid, it probably is. And so you can correct yourself and say, no, wait a second, did I say that? It's a very good way of learning. Just try it, and you'll find it. Now, a thing that we emphasize here, that we have a code of conduct, and I've had some unpleasant experiences with people cheating in the class, and, not so hard to catch them. And I flunk people, and it's very unpleasant for me, for them, because they have to go home and tell their parents, I flunked physics because I was cheating. That's not a pleasant thing to have to come home with at the end of the semester. So don't try. But cheating is not working with somebody. Cheating is putting your name on some work that really was somebody else's. Don't do it. It's not worth it. Believe me, it's just not worth it. Now, we have the textbook, which I think is pretty good. It's quite good. He's boiled everything down to the minimum, pretty much. Maybe too little, because every word counts, and you have to read it rather thoroughly. But if you do, you'll get it. Now, don't try to get through the course without reading the book. I've had some people say, I just never read the book. No, that's a very bad idea. Read the book, hopefully before you come to class, because then you'll understand what I'm trying to say, because I won't say everything that's in the book, and you don't have to, in fact, know everything in the book. But at least it'll give you a feeling for what's going on. But in addition to that, we're being recorded right now, at least I am, and the PowerPoints are recorded and will appear on what's called webcast. So you can always go back and hear what I've said on this particular online facility. In addition, there are some nice books other than Wolfson that I like. There's what is going on here? It's a very sensitive machine. This book by Hewitt, who was a professor at, I think, USF, and he even draws his own cartoons. It's cute. And Giancoli was a professor here, wrote a very nice book. Richard Feynman is a Nobel Prize-winning, interesting guy who wrote lectures in physics for his Caltech undergraduates. And it's even the professional physicists read Feynman to learn something, because he has his own interesting, different, kooky way of looking at things. But the problem is sometimes hard to find what you're looking for, because he doesn't have the standard way of organizing things. And then there's a very good book by another Nobel Prize winner, Edwin Purcell of Harvard, Electricity and Magnetism, which is very nice, very clear, deep book, and that's very good. Then there's a lot of stuff online. There's a professor that recorded his lectures, and there's the Khan Academy. How do they do now? Sorry, folks. I got onto the Harvard site. Let me get away from that. What's it going to do? Come on, guys. Whew. Wow. Oh, PowerPoint quit. Okay. Start again. to have it twice now. Okay. Sorry about that. We'll go ahead. Okay, resources. Oh, and also I found out just yesterday, you may know about it, there's something called academic services where you can get tutoring from another student. I guess it's a free service that the university has dug up. Yeah, have you ever tried it? Well, you might try that. Just go to that website and you can find it. And of course, there's myself and the GSIs. My office hours are before class, like 1 o'clock till 2, and I stay after class as long as anybody wants to talk. I've sat here till 6 o'clock. We just talk about things. So you can do that, or write me an email if there's something bothering you. The GSIs, I think you'll find very helpful as well. Okay. By the way, you can interrupt me at any time and ask questions if something's not clear. Now, this is funny. Here you are, college students, and I put in this little slide because I think we should appreciate what we're doing here. See, it's a method of thinking that puts observation as the primary decider of truth. Now, when you think about that, that seems pretty obvious to us as science students. But that's not, is it really obvious that we should have that privilege? Not everybody puts observation and what the facts in front of you and checks the facts before they come to what they believe is the truth. That's a new idea. And in times past, if you did that, you might get burned at the stake. Or you might get shot in the face. So this is a privilege. I think we should appreciate it. And I think that the way of doing this kind of thinking is very good because the idea of science is that you're skeptical of everything, including me. I mean, you want to challenge me if I sound like I'm saying something wrong. I'm not infallible, far from it. But you want to challenge everything you hear. Really, that's the scientific approach, to be skeptical, and that's actually more important than any fact you're going to learn. But we also have the idea here of trying to be as quantitative as possible. That is, put numbers on things. That's a challenge too. Not all of us are so comfortable with that. But I think it's a very good thing to do. For example, have you heard about the incident in France in the last couple of weeks? Anybody not heard of this? Okay. So put some numbers on it. How many people roughly were killed in that incident, would you say, roughly? Anybody know? What? Around 15. Yeah, it's around 15. Let's call it 20, ballpark. Okay. And it was called a major terrorist attack, and people are doing this and that, and the governments are getting all excited. Okay. Now, does anybody know how many people were killed in automobile accidents in France that day? Pretty close to a lot more. Well, no, that's pretty good. That's a question you want to ask. I mean, what are we comparing this to? What? Look, I'm not making a political speech, or maybe I am. But the idea is, what should we be terrorized by? Should you be? So, okay. Actually, the number I looked it up. There are roughly 3,000 traffic fatalities in France in a year. Their population is less than ours, about 60 some odd million. We have 300 million. We have 36,000 a year. So let's say we divide by roughly 300 days, 350 days. Let's keep it simple. Okay. So that's around 10 traffic fatalities in France a day. That incident took 2 days. They killed roughly 10 people a day. So that's the same as if they had traffic accidents that day. Here in America, we have 36,000. If you divide that by, say, 300 days, well, we're a bigger population, but we have, we have 120 per day. Or roughly, actually, that corresponds to, if you have 12 months, it's 3,000 a month. Traffic fatalities in the United States, 3,000. That's how many people were killed in the 9/11 attack, 3,000. And we have that every month on our highways. Every month since then, roughly 3,000 people killed. So the question is, of what should we be in terror? Should we be worried about being bombed, or should we worry about getting in our cars? According to, that's trying to think with numbers. And I think it's a good way to think once in a while, at least. It doesn't say, well, these are worse deaths and those deaths, and there's all kinds of other maybe feeling things that go on, political issues and so on. But if you can think quantitatively once in a while, or try to cast the problem with numbers, it puts a different light on things. And you'll never hear a politician talk like that, by the way. Have you ever heard that before? They won't. But think of how much money was spent trying to fix this problem, the terror problem, compared to fixing our highways or making our cars safer. I mean, suppose you put $100 billion into making cars safer. How much would that save in lives? So, you're citizens, so you want to think good, think good ways. Okay, let's move on from politics or numbers to more about physics. Now, I like to start out with what we do not know, because I don't want to give the impression that science knows everything. We don't. And in this course in particular, I'm just going to throw things at you like electric charge. We don't know why it is, why it's always the same, why it has the magnitude that it has, why isn't it 10 times bigger, 10 times smaller, why there are only two types, plus minus, if we call them, why is the universe overall neutral? We don't have more plus than minus. We don't know. Lots of questions like that we don't know. But there is a possible answer in that if things were much different, like if there were no electric charge, what would the universe be like? Well, we wouldn't really exist, because it's the electric charge that keeps materials together. It's an attraction that keeps things together. So we wouldn't even be here to ask the question. So somehow the universe figured out that this particular arrangement, this particular set of physical properties allows something to exist. That's about the best we can do. But these very deep questions, nobody knows the answers to. And I don't even know anybody who's trying to get the answer. Maybe they are. But anybody who's trying to get the answer to these questions is quiet, because people will think he's crazy. Why is he worrying about that? Why isn't he doing something else useful? Okay, so we don't know a lot of things, but we do know, amazingly enough, we do know quite a lot of things. And what is amazing is that even the few simple things, now physics actually, I don't know what your experience in 8A was. Oh, by the way, how many of you had a physics course before in high school even? Oh, a lot. And who has not had every physics before? Anybody? A few. Okay, we will start at the beginning. But I think that physics maybe has a bad reputation, that it's complicated, hard, mathematical. It doesn't have to be. The fact is that unlike biology, which I find very difficult, because there's a lot of things you have to know and they seem to be all separated and so on, and chemistry, sulfur is like this and iron is like that, and it's hard. But physics, if you know a few basic things, you can sort of figure out everything else. It's a little like geometry. In geometry, you learn like 10 axioms. And then they built up this gigantic structure on these 10 obvious axioms. That's amazing. And physics is like that. I think that's what attracted people like Einstein to physics. That and Magnus, he talks about. Well, I'll show you Magnus later. But physics, if you learn a few basic principles, you can pretty much figure everything else out just sitting there to a very good approximation. Then if you want to do the numbers, you can you can do the numbers if you can, or else you get a friend to do the numbers. But you can get a pretty good idea of the thing. Now, I will give you an example of some simple ideas like Newton's laws and how they produce an extremely amazing result. Let's see, I want to go back, I think. And again, I think the method of thinking, namely skepticism, is the key thing that we can learn here. And I asterisk think we know these things because the one thing about science is things could change. I mean, it could well be that we'll find out that all electrons are not alike, or that Newton's law doesn't work everywhere, or that energy is not conserved. So far, we think that it is. The evidence is very strong. We've tested a lot of these things many, many times, and it looks right. But one thing that lurks in the mind of all scientists is, I'm going to overthrow Newton's law. They plot that, in their mind. I'm going to overthrow Newton's law. Then you're a hero. On the other hand, in the meantime, we use it. and we, make a living using Newton's law. But you keep hoping that someday you'll figure out why it's wrong and make an improvement. Einstein did it, of course. He was pretty good. So everything is subject to change, and we question everything. Please do. Now, here's another point that I want to make. You're not here voluntarily. I know not everybody rushes in to take a physics course. But the thing that you want to do is try to learn, pretend that you're a child and haven't learned anything up till now, and try to learn things from the beginning. Because what I find is a lot of people come in with the preconceptions about how things work. They think they know what a force is. They think they know what energy is. You come in, like, I'll give you an example. When I was a kid, my parents used to refer to electricity as a juice. You plug it into the juice. Do your parents ever talk like that? They were not physicists. My parents were not educated in that at all. And, we come with these funny ideas from hearing things. So I'd like you to sort of wipe the slate clean as much as possible and try to think clearly, like, I don't know, let me see what this really means. Again, this is skepticism even about yourself. Now, what am I going to do here? Well, I ask you to read the book because the book is good. And one thing you should understand about a lecturer is that I talk pretty much extemporaneously. I don't read from a script. Wolfson wrote every word down carefully. Somebody edited it. He revised it. Those words are perfectly carefully chosen. So his text is much better than my speaking. Accurate, concise, perfect. Very good. I'm blabbing on, and so I can't help you that much. But what I can do is I can emphasize certain things that I think are important and try to embellish them and put some juice into it. This is a very dry kind of book. I'm going to try to put some juice in the course. And also to make connections that he doesn't make sometimes, because he's going down a list of topics. So I think I can help you some, but you know how to learn. You're pretty much on your own. Now, the other thing I like to tell you, because some of you are going to medical school, hopefully, and you want to think of it that this method of approach to physics is the same as a doctor would use. A person comes in with symptoms. So a physics problem will present with certain givens, facts, or ideas. These are symptoms of the problem. It's actually much simpler than what a doctor faces, because a person comes into a doctor and he's got a rash or fever, but there's all other things that the person doesn't even know that he has, like blood pressure and so on. In the physics question, we're going to say a mass of 2 kilograms falling at a speed of blah, blah, blah. We're giving you the symptoms, clearly. So we're setting it up for you. In real life, it's much more complicated. But basically, a physics problem is a set of symptoms, conditions. And you have to sort out what are the important symptoms for this problem. Then you have to analyze it and find out, what am I dealing with here? Like a doctor would have to say, well, is this a fracture? Is this a blood pressure problem? Is this a stroke? What am I dealing with? So you analyze the problem. You treat it. Physics-wise, you would presumably plug into some equation or write an essay about how I would treat these symptoms. You have to analyze it to get the right disease. And then you see if the treatment worked. So you go back and you look at your solution, and it does it see if it makes sense. In the case of a doctor, he'll say, take 2 aspirin and see me in the morning or something, and you come back and you're feeling worse. He says, well, I have to try something else. So you go back to the top, analyze again, and go down the thing until you get it. So I think this method of thinking is very valuable as an approach to whatever you're going to do. This is not exclusive to physics or medicine. I think this is just a very intelligent way to do things. Now we get to one of my, unfortunately, pet peeves, and I alluded to it before, and that is you come into this class with certain conceptions about what words mean. And the problem is that the use in physics is very specific and well-defined, or else we don't use the word. In fact, here's a case where, you'll read knowledgeable things like the Merriam-Webster word of the day. There's a service you can sign up for. They'll send you a word, and you can learn a new word. And they said, what is a 6-letter descendant of ergon that is a synonym of power? Now, could you guess what word derives from ergon that is a synonym of power? What they came up with was energy. Energy comes from the erg. But they say that's a synonym of power. Maybe to them it is, maybe to Merriam and Webster, but it's not to us. To us, physicists, energy and power are 2 distinctly different things. As you should know now from 8A, but I'm going to emphasize that a lot, and especially because if you ever read your PG&E bill, anybody read a PG&E bill ever? You ever pay any? Do you know what they're charging you for? Energy or power? No. You should know. You're paying, actually it's energy. In fact, they say it right. How do they put it? They have a slogan. It slips my mind. We deliver power. We deliver energy or something. We deliver energy. See, we speak of them as power companies, but what they really sell us is energy. It's good to know, and we will. You'll by the end of this course, you will know that, or else, you will know that. And here's another one, another misuse of scientific. This one is really interesting. This was only a couple of weeks ago, on January 12th. The New York Times. This lady, Rivka Weinberg, is a professor at Scripps College down south, and she wrote an op-ed in the Times. I don't know if you can read that. And there's a conversation between Zigan and Schumacher. Einstein said, in the world there is time, and just as there is time, there is another thing, space. Space and time, time and space. And these 2 things, he said, are relative. So the guy says, so what? What does it mean? So he says, do you know what relative means? And Zigan says, the blue thing, I've made it blue. There is no person these days who doesn't know what relative means. Well, she doesn't know it, because she says, I'll explain it to you with analogy. You soon will know. Relativity is like this. If you have 7 hairs on your head, it's too few. It's very few. If you have 7 hairs in your soup, it's very many. So that's relative. Now, that's a joke, but it's not relativity. It's something else. Relativity has nothing to do with this. Nothing. Einstein never said anything vaguely like that. And he had a lot of hair, so maybe he didn't have to worry about it. But, no, the point is, you will read all kinds of stuff, especially about relativity. And the other thing that you'll hear nonsense about is the uncertainty principle. You heard of the Heisenberg uncertainty? Misused all the time. We'll get to that. We'll get to both of these. But it's nonsense what you'll hear. And so you have to learn what we mean in physics by these words. And you cannot use the street meaning. Just don't even try. Try to learn the exact meaning. And now we have Newton's laws. This is the basic. This is what you should have learned from 8A. If you know these 2 ideas if you're an educated person in the Western world, you have to know Newton's laws. Sorry to say. If you walk out of this university not knowing Newton's laws, we have failed. The first law is the law of inertia. Very not obvious law. Anybody know what the law of inertia is? You remember? I'm not letting you out of the school. No, the law of inertia is it's kind of strange and obvious at the same time. It says that if I have a body that's moving in a straight line, and if you don't do anything to it, if it's moving with a constant speed in a straight line, it will keep on moving forever. Now, why is that not obvious? It's not obvious because it never happens in your life. If that's moving in a straight line, it does not move forever. Nothing you've ever seen moves in a straight line forever, right? So why is that a law of physics? Well, it's because, think of it why it's obvious. If the thing is moving along and nothing is acting on it, why should it go to the right? Why should it go to the left? Why should it not just continue going? So in a way, it's obvious that a thing will keep going in a straight line forever because there's no reason for it to go any other way. So by that kind of a symmetry argument, you can say that that law is obvious. And that's what Galileo and Descartes, way back about 500 years ago, said. And that's a very, very important idea because it says, the next thing says, that, this idea here is that, first of all, you don't need a force to make things move. For example, the Greeks had an idea that the sun was being moved across the sky, being pulled by a chariot of Apollo's and his horses. They thought that in order for something to move, you have to keep pulling on it, which in a way we do. I mean, if you're in a car, you have to keep pressing on the gas or else it'll stop. But the point is that if you understand the law of inertia, you realize that what's really happening is that there's some external forces acting on the thing, and those external forces are causing acceleration. Acceleration meaning change in speed. That's so important. That's a revolutionary idea. It sounds so simple, and it is. That's what I meant by physics is that simple. But you just got to look underneath and see how fantastic that is, because on top of that, you build a whole science. Up till that, it was just a mess. Up till 500 years ago, the smartest people in the world didn't understand it. Aristotle, Socrates, Plato, all the great guys, Archimedes, all wrong. 500 years only do we know this. Now, look what that allowed us to do. I don't know if you heard of this one, where the Europeans shot up a rocket ship, which was supposed to rendezvous with a comet. The comet was, let me see if I can get it, was way out here when we saw it in a telescope. And some guys got the right idea, why don't we shoot a rocket ship and land on that comet? I'm sorry. This is a very sensitive machine. Oh, sorry, I'm going the wrong way. Wait a second. Oh, okay. Gosh. Okay, let me try to get out here. So I just follow my finger. I think, can you read, the dotted line is the orbit of Jupiter. Jupiter is way out, so that comet was way out by Jupiter when it was first noticed. So the guys realized that it would take years, like 10 years, for it to come all around to about there. So they got the idea to shoot this is all, and what I'm trying to tell you here is that all they use is F equals ma. And they did this prodigious thing. Because if you know the forces, and you know this is the force of gravity working, right? Because your rocket ship is under the force of gravity, unless you push it with rockets a little bit. But mostly it's gravity working. So the gravity of the sun and the other planets. So, just using F equals ma, they figured out how to intercept the comet 10 years later, rendezvous with the comet. See that point over there? So what you had to do, You shoot the rocket out of the Earth. You see the upper right there, it says Mosetta launched in March 2004. It was launched off the Earth. It circled around the sun, circled around the Earth again to pick up yet more speed because they couldn't give it enough speed to catch the comet. They circled around the Earth twice to sort of pick up speed, knowing the force of gravity from the Earth and the sun, all that calculated. Went around twice. Rosetta came around, and in November, it ended up 60 miles from the comet. Could you believe it? I mean, that's amazing. And then well, that's close enough. And they adjusted it a little bit. And did you follow the story at all? Did anybody follow the story? Well, actually, what they had aboard it was they wanted to latch onto it. So they actually they came closer to within about 20 miles. And then they shot a little grappling thing to grab the comet. So right now, there is this grapple thing holding on to the comet and doing experiments on the comet. And it's all from F equals ma. By knowing the acceleration, you could guide this thing. First, they had to know how fast to do it, how to circle around the Earth to pick up speed, just when and where. So we had to know where the Earth was. It took them 10 years to catch it, and it traveled, I think it says, 6 billion miles, and ended up 60 miles away. I mean, that's numbers for you. It's just fantastic. And the beauty part is that, so what you have to know is the forces that are acting. And then you just put it in that F equals ma, and you can do wonders. You can, so in 8B, now in 8A, you learned about gravity somewhat, like dropping things and so on. So there's a force. But here we'll do electricity. And what I've done for you in these notes is I try to break it down because there are big ideas and there are lesser ideas. The big ideas are numbered. Why does it skip from 1 to 3? That's the bad. What happened there? Okay, it's 1, 2, 3. There's only 3. Big ideas. The electric charge, the forces on the electric charges, and the electric field is a concept. Electric field is actually subsidiary to the forces. It's actually derived from it. So the point is that we're going to be dealing here with forces that don't contact each other, or when things don't contact. And you've had this before, of course. Gravity is a force that, where there's no, for example, there's no contact between this chalk and the Earth. And yet the Earth causes it to move, accelerate. So it exerts a force on it. That's one that you're familiar with. You might not think of it that way, but the Earth is exerting a it's not even a force you can shield. We have no gravity shield. You can't stop gravity. And it's a non-contact force. The other one that you're surely familiar with is magnetism. This compass needle is pointing north-south, and it's a non-contact force because there's another magnet, and I can make, let me try this one, I can make that, I'm not contacting it, right? And this is a mysterious thing. So these are non-contact forces, very mysterious, but they're there. And again, we don't know exactly why this exists. As I said at the beginning, this is one of the unknowns. Why is there gravity? We don't know. But we know it well enough to plot those orbits very well. And all we put in there was the force of gravity. That's all. And, of course, there were some rockets on the little probe to make adjustments, but it was mostly gravity. And we know gravity very well. Gravity has that particular form and force. Now, the third force that we deal with on ordinary scale is electric force. And this was first discovered really by frictional things. Like sometimes you may have had the experience of sliding into, well, in the Bay Area, it doesn't happen very much because it's kind of humid. But if it's very dry, like very cold, I come from the East Coast, and there in the winter there's not much humidity, and the air gets very dry, and the static charge builds up on things. You walk across and you get a little shock sometimes. I don't know if that's happened to you. Well, that's where people discovered electricity. It's kind of a freak thing. So by friction, you can sort of rub electric charge apparently off of things. And you see, I can make this thing be attracted here, non-contact. It's not the wind. I think not. That's another of our non-contact forces. It's amazing, isn't it? I mean, it's shocking. In fact, if you really want to know, there is two things never contact, as much as you'd like to think so. Because the electric force is so great that when things get really close, there's always space between, and things repel. So nothing really unless you have like a covalent bond or something. Okay, so there's one effect that I want to point out to you. Let's make a little chart here quickly. So the first experiment was I sort of put some charge on here, and I had this thing on a balance, and it was, would you say it was attractive or repulsive? Attractive, okay? So that effect is attractive. Okay, now let me do a second trick. Let me take the same thing that I put charge on this one. Let me put charge on this one without hurting things too much, if I can a little bit. So now, so, let's put that one down. So I have charge, and I've done the same thing. So presumably it's the same charge on both, right? And now I get repulsion. Okay, that was the. Let me see, which one did I think I did this one, right? Yeah. Okay, now it turns out that we can get a different effect by using a different material to rub the, this one has no charge on it, I hope. Oh, but this one has charge on it. Okay. Well, let me try with, so remember that's the plus guy has some charge from the plastic. Now let me do this cat's fur. Who's somebody's fur. Hopefully humanely treated. Okay, now, let's try with this guy first. He's very, very attractive. Okay, so let's put down, now let's say this is with the fur, say, okay? And this is with the charge. Okay, what else can we... And this was, again, where is it? Plus, where are you? Here. They're strongly attractive, right? So that's attractive. These are the kind of things people did around 1700. So we're starting at the very beginning. Now, what else can we do? So now let's try this. Here's the one that the furry guy, and let me try to. This one I didn't put anything on yet, right? Is it not going to do something? Yeah. So this one is uncharged, but it's nevertheless attracted. Okay, so yeah, so what we had here, we had a furry guy. Oh, and again, what did I do here? Okay, the one that was never charged, but no, I didn't do that. This was charged with the plastic. Let me say plastic. But the furry one was attracted to the uncharged, so you have attraction. So those are the kinds of things we're playing with, and we have to figure out. So what it turns out, very simply, is that in this case of this experiment, we have different kinds of things. We have these several different kinds of non-contact forces. We have the gravity, which we live in, magnetism, which we know about, and now this electric stuff. Now the idea is that the way this works is that there are two different effects going on here, frankly. Hope you can see this. There's the one effect where if you have some charge, it could either be the plastic or the fur. If you go to an uncharged one, you will get attraction. This will be the result of, you can see if you can piece this together from what we just did. If you have like and like if I put plastic and plastic, you get repulsion. If you put plastic and fur, you get attraction. That's the result. I think if you go back over what we did, that's what happened. So that's the idea of something has been transferred from the plastic to these styrofoam balls. And we call that thing that is transferred, we call that electric charge. Now again, we want to use the words properly. It's not a charge card. It's not a charge of the light brigade. This charge here means a quantity of something. And my nearest analogy is to a quantity of, say, water. Electric charge is, if you want to think of it as sort of a quantity like water. A quantity of water like a liter of water. Or a mole, it's more like a mole of water. A mole is a certain number of molecules. The charge is a coulomb. It's a certain number of elementary charges. Just as a mole of water has Avogadro's number of molecules, a coulomb of charge has a certain number, 6 times 10 to the 23. There are 6 times 10 to the 18th elementary charges of E in this large quantity called a coulomb. So that's what you want to think about. Some stuff has been transferred from the plastic or to the styrofoam, or from the fur to the styrofoam, and there seems to be two different types because sometimes we get attraction and sometimes we get repulsion. Now the more mysterious one, let me break the mystery down. The reason this works, even though this has no charge to start with, because the charges there are electric charges inside this, but they're neutral. You have as much plus as minus. We call these plus-minus charges. We could have called them Sam and Mary. Plus and minus has nothing to do with anything So what would happen here, if I bring a charged thing here, let's say, for the sake of argument, some minus charge on this rod. If I bring it near here, the minuses repel each other. So the minuses are going to try to go to this side, leaving behind the pluses. So that means that the pluses are closer to the minuses. And because they're closer, they'll attract. So that's why you get attraction even when this thing here is overall neutral. Neutral meaning it has no net charge. But this one has a net charge, and we call that an induced attraction. See, these, when I put charge on these things, I've really transferred some electricity to each of these, and then they do their thing. But even if the thing is neutral, as we call it, it still gets attracted. Probably not as strongly, because in this case, I've really put something on here. Like, let's say I put minus, 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 and minus, 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 minus. It's going to be very strong repulsion, because minuses, it turns out, don't like minuses. On the other hand, if I have pluses and minuses, that's going to be a strong attraction, right? Is that okay? So I'll leave you with this thing, Valley Talk, because I love this, that it's like, you know how people sell out, some people, everything is like, it's like I did, yeah. So it's like likes like each other, and it's like unlikes dislike each other. It's like that. Okay.